Guys, I wanted to do a video here on the first topic in Focus 11. This topic covers some basic ideas in spectroscopy, and so these are general concepts that we need to understand the more specific topics that we'll study later. So, as you already know, spectroscopy involves the interaction between matter and electromagnetic radiation, and typically what you look at is the intensity of radiation, either absorbed or emitted, as a function of the frequency of the light, the wavelength, or and other times you look at the wave number of the light. And so what I've got here on the slide are three basic motifs in spectroscopy. The first one, you're probably already familiar with the terms absorption and emission. Here you have, in the case of absorption, a photon is absorbed by matter, and in the case of emission, a photon is produced by matter. And the equation that I've listed here is the resonance condition that we've looked at previously, which relates the energy of the photon, here expressed as h times frequency, or you can express it in terms of the wavelength of the photon, or the wave number of the photon. That photon energy is equal to a change in energy in the material system. Okay, so in the case of absorption, the photon's energy is added to the system, and so the molecular energy goes up. In the case of emission, the photon that's produced, that energy is lost by the system, and so the molecular system's energy goes down. Another motif in spectroscopy involves the scattering of photons by matter. And so in this case, photons interact with matter, but the photon isn't absorbed. What happens is the photon comes in, it interacts with the matter a little bit, the matter's energy may change, and then the photon will leave the system in a different direction. So it's scattered off in a different direction. Sometimes the photon's energy stays the same. Sometimes the photon's energy increases, and sometimes the photon's energy decreases. But the photon isn't created or destroyed in the process. It's just scattered by the matter. And so we can classify that broadly in two ways. You can have elastic scattering, where the incident photon's energy, that's this h nu naught, is equal to the scattered photon's energy. Okay, so that's elastic scattering. There's no change in the energy of the photon as it scatters. And nothing happens in the material system in that sense. On the other hand, you can have inelastic scattering, where there's a shift between the photon's incident energy and then the outgoing photon's energy that it has left. And so the photon isn't completely destroyed, but some of its energy may be consumed, or it may actually pick up some additional energy from the material system. So this delta E can be positive or negative, depending on whether the photon gains or loses energy. Anyway, we call that inelastic scattering, and so we'll talk about that on the next slide. I think I have a figure illustrating it, but before then, this third point here. You're actually already familiar with resonance spectroscopies. I'm sure you've studied nuclear magnetic resonance before. That's a type of resonance spectroscopy. We won't cover that in any detail in this chapter, but we will have a separate chapter on nuclear magnetic resonance. So we'll come back to this point. So here's the figure that illustrates scattering of photons, and so this is called Raman Spectroscopy. It's named after a person. So imagine that you've got some energy levels here in your material system, and then you shine laser light, for example, on the system. You can imagine that the system gains that energy, but then very quickly it comes back down. Okay, and if the system comes back down to the exact same energy level, you would have, and then the photon goes off in a different direction, you would have what we identified previously as elastic scattering, and a synonym for that is Rayleigh scattering. On the other hand, when the system crashes back down, it could go to a higher energy level than it was before, and this we call the Stokes scattering. Alternatively, when it comes back down, it could come back down to a lower energy level, and this is called the anti-Stokes scattering. We will work with scattering in more detail in the following sections. So for example, we'll look at Raman microwave spectroscopy, and we'll look at Raman infrared spectroscopy as well. This is just a very general slide. It highlights that spectroscopy is a very powerful tool for interrogating the composition, structure, and dynamics of material systems. And what you want to take away from this, this is something that you actually do want to know. You want to know what regions of the electromagnetic spectrum are connected with what types of molecular transitions. So, for example, radio waves are resonant with nuclear spin flips in NMR. Microwave radiation is resonant with molecular rotations and electron spin flips. Infrared corresponds with molecular vibrations. UV and Vis correspond to electronic excitations involving valence electrons. X-rays would excite core electrons within molecules. It's also used in X-ray crystallography in a scattering type of motif to determine the structure of crystals. And then the gamma rays, those aren't so useful to chemists. This is more the domain of physics. Gamma rays are resonant with transitions that occur within the nucleus of an atom. So we won't really have anything to say about that. But we will look at different aspects of many of these. Okay, on this slide, what I'm doing is introducing a basic model that we'll use. It's very simple. The TwoState Model is a simplified model for considering what happens in a spectroscopic process. So we have two energy levels. We have a lower energy level E1 and an upper energy level E2, and they have these populations. That means if you look at the whole population of molecules in your sample, N1 of them are in the lower state and N2 of them are in the upper state. And the ratio of those two populations is governed by statistical mechanics and something that is referred to as the Boltzmann distribution. And so what the Boltzmann distribution does is it allows us to calculate the ratio of molecules in the upper state versus molecules in the lower state. Here's the Boltzmann distribution function. That ratio is proportional to the exponential of minus the energy difference between them divided by the thermal energy. So KT is the average thermal energy in the system. And if you take the resonance condition, that is the energy difference in the material system is equal to a photon energy, you can write the Boltzmann distribution in this fashion. And what you find at a given temperature, the larger the energy difference between the two states, the smaller the population is in the upper state. And so we'll make use of that several times as we encounter different types of spectroscopies. This next set of slides considers three elementary radiative processes. And so these are fundamental processes that can occur when you have the interaction between photons and matter. And what we're going to do is simply explore the relationships between them a little bit. It's a little esoteric, but it's worth it in the end, just to give us something to think about in terms of these different processes. But the most important thing are really just knowing these three bullet points. That is, knowing what absorption is, knowing what stimulated emission is, and knowing what spontaneous emission is. So let's go through that in some detail. Stimulated emission or stimulated absorption is just regular absorption. What happens is an electromagnetic field drives a transition from a lower energy state to a higher energy state. Stimulated emission is essentially the opposite of that. You have an electromagnetic field that drives the state from a higher energy level to a lower energy level. And in the process, that produces another photon of light. And that photon that's produced has the same frequency, the same phase, the same polarization, the same direction of propagation as the original photon. And so those two photons will then add together. So you'll go from just one photon to two photons, and the light that's produced is said to be coherent. At the very end of this chapter, we'll talk about lasers, and lasers involve stimulated emission. Another type of emission, the one that we're probably more familiar with, is called spontaneous emission. And this is a process that happens all on its own. It's the result of quantum fluctuations involving the vacuum electromagnetic field. And basically it means that excited states are intrinsically unstable, and what goes up must come down. And so you basically have a spontaneous transition from a high energy state to a low energy state. Now in this case, the photons that are produced are incoherent. That is, when a sample is emitting photons, the photons that are emitted have different directions of propagation. They have different phases. They have different polarizations. This is what is meant by the classification incoherent light. So these three processes here can be thought of as little chemical equations, elementary equations, in fact, much like the ones that we worked with in Chem 450 when we studied chemical kinetics. And so I've outlined these three equations here. This is the elementary chemical equation for absorption. You have a molecule in E1. It absorbs a photon. There's a rate constant for that process to occur, and then the product is a molecule in the upper state 2. For stimulated emission, you start off in E2, and then a photon comes in. There's a rate constant. You then crash back down to state 1, and then another photon is produced. Really, I think I should probably have a stoichiometric coefficient of 2 here in front of this photon, just to know that this reactant photon isn't actually destroyed in the process. It continues on. So there should probably be a 2 here in the products. For this last one, it's the equivalent of a unimolecular process where you have just one reactant here, the excited state, and spontaneously on its own with a certain rate constant, it crashes back down to the lower energy state and produces a photon in the process. So we can consider these to be elementary type chemical reactions. These are their rate constants, and you might expect what we're going to do next is look at the rates for these different reactions. And in fact, that's what Einstein did. He articulated the rate laws governing absorption and emission. And so on the left-hand side here, we have the rates of each of these processes. And like any elementary rate law, the rate is equal to the rate constant times the concentration of the reactants. So N1 is the population of state 1, and it represents the concentration of molecules in that lower state. This rho nu, this is called the spectral energy density. This represents the concentration of photons with a particular frequency. And you can do the same thing for the stimulated emission rate and for the spontaneous emission rate. In the case of the spontaneous emission rate, there's only one reactant, and that is the excited state molecules, and so N2 is the concentration of molecules in the excited state. Now, if this system were to come to equilibrium, meaning that there's no net change in the populations as a function of time, then the rate of absorption must equal the sum, the total emission rate, so the rate of stimulated emission plus the rate of spontaneous emission. So this is the equilibrium condition. And what Einstein did was he used this equation to characterize the rate constants. Okay, so these are actually called the Einstein A and B coefficients. And in the next slide, what's done is a little bit of manipulation. So that equilibrium equation is solved for the spectral energy density, and so you get an expression that looks like this. And then what you can do, really, you could have any spectral density that your system has, but in this particular case, we're going to assume that the spectral energy density is given by something that we've seen previously, the Planck black-body distribution law. And so that has this form. This is an equation that we've worked with previously at the very beginning of the course. And we're going to make some identifications. So we're going to compare this equation to that one, and then we'll use that to specify the relationships between the rate constants. So using the Boltzmann equation, this ratio can be expressed exactly as this exponential. So the first identification is relating this ratio with that exponential. Well, once you make that identification, it's very natural to equate this ratio with the number 1. And so what we're doing is we're saying that the ratio of stimulated emission to absorption is unity. And while we're at it, then we'll identify the numerator here, this ratio, with the what's in the numerator here. Okay, and that gives us these relationships. So what we found is that the absorption rate constant equals the stimulated emission rate constant, and that the relationship between the spontaneous emission and the absorption rate constant is given by this expression here. One thing that we can do with these rates, is to calculate the ratio of emission versus stimulated emission. So for example, I've got a system that's emitting photons. How many of those, what's the fraction of those photons that are coming from stimulated emission versus the fraction that are coming from spontaneous emission? And so that's expressed here in this ratio. So taking the rate laws and calculating the ratio, you get an expression that looks like this. And what we note is that the ratio of spontaneous to stimulated emission depends upon the frequency cubed, in fact. And what that tells you is that at higher frequencies of emitted light, the bulk of the emitted light will be spontaneous, but at lower frequencies, when nu is small, then more of the emitted light will be stimulated emission. Okay, and so this next conceptual problem asks us to discuss that. So we're considering the relative importance of spontaneous versus stimulated emission in IR versus UV vis spectroscopy. And the hint here is that we are to note that UV vis radiation has roughly 100 times the frequency as IR. So going back to the equation here, for UV vis, this number nu is 100 times greater than it would be for IR. And so that tells us that for UV vis, the spontaneous emission is going to be dominant, whereas for infrared, the stimulated emission will be more important. Okay, so this next subtopic here involves the selection rules of spectroscopy. We've talked about selection rules previously in the context of atomic spectroscopy. We're going to talk about selection rules for each of the molecular spectroscopies that we look at, and so at this point it's a good idea to just kind of review a couple of features of selection rules. So first of all, what selection rules do is they articulate whether or not a given transition can occur. So not every transition that you could imagine in your molecular system is possible. You may have energy resonance with a photon. That is, you've got the right frequency of light, but that doesn't necessarily mean that the absorption is going to occur. Resonance is a necessary condition, but it is not a sufficient condition. The other thing that you need in place in order to have a spectroscopic transition, you need to have a oscillating transient dipole moment that's oscillating with the same frequency as that radiation. And so that transition dipole moment is given here by this integral. So this is the transition dipole moment between two states, I and F. And this mu hat is the dipole moment operator for our system. And that is placed between the initial state and the final state wave functions that we're considering. And you integrate over all space for your particular molecular system. And if this integral is non-zero, then we say that the transition is allowed. And if it is zero, we say that the transition is forbidden. And by analyzing these types of integrals, you can arrive at two basic types of selection rules. One is called the gross selection rule, which tells you what are the general features of the molecule that you need to have in order for the molecule to, say, absorb a particular type of radiation. For example, we will look at microwave spectroscopy in the next section, and in order for a molecule to absorb microwave radiation, it must have a permanent dipole moment. If it doesn't have a permanent dipole moment, then you can't use microwave spectroscopy, or at least absorption spectroscopy, to study that molecule, because it just doesn't absorb. So that's what we mean by a gross selection rule. What are the general features of the molecules that need to be in place in order for that spectroscopy to work? The specific selection rules are expressed in terms of quantum numbers of states. So what is the quantum number of state I and the quantum number of state F in order for this to be non-zero? This often involves various aspects of symmetry, as we'll see. This is an example of that from atomic spectroscopy. So you may or may not recall, but the selection rules for atomic spectroscopy is that the angular momentum of the state must change. So for example, if you were to consider a 1s orbital here and a 2s orbital here, this transition is not allowed because the orbital angular momentum quantum number doesn't change as you go from a 1s to a 2s. And so this is an unallowed transition, whereas this transition here between, say, a 1s orbital and a 2p orbital is allowed because there's a change in the angular momentum quantum number. And so that's the specific selection rule for atomic spectroscopy, or at least one of them. And it allows you to distinguish between allowed transitions and forbidden transitions. The next topic here is, it's an interesting topic. It's more experimental, the way it's cast here. The Beer-Lambert law is an empirical relationship between the incident light and the transmitted light through a sample. So here, the transmission is defined as the ratio of the transmitted intensity divided by the incident intensity. And experimentally, it's shown to have this anti-logarithm dependence, 10 to the minus epsilon, where epsilon is the so-called molar absorption coefficient. In other sources, it's called the extinction coefficient. J in brackets here is the concentration of whatever absorber you have in your sample. And L is the path length through the sample. You can convert the transmittance to a so-called absorbance by taking the logarithm of both sides. So the logarithm base 10 of this ratio, and then you do a little trickery here with the minus sign. It gives you the absorbance as the molar absorption coefficient times the concentration times the path length. this equation here is used in this problem. And so really they're just having us explore the Beer-Lambert law. So you've got radiation at 280 nanometers. You've got a 1 millimeter path length. Your absorber is the amino acid tryptophan, and that has a concentration of 0.5 millimoles per liter. Under these conditions, we're told that the transmittance is 0.54, and then we are being asked to calculate the absorbance and the molar absorption coefficient under these conditions. So what I've done here is I've taken the this is the Beer-Lambert law, and the ratio I0 over I is the reciprocal of the transmittance. So I've set that equal to 1 over 0.54. Take the log base 10, that gives you the absorbance at this frequency. And then what I'm doing next is I'm using the other side of the Beer-Lambert law, rearranging it and solving for the molar absorptivity coefficient. And so you plug in those numbers, and this is the number you get. In a follow-up problem, they asked us what would be the transmittance if we doubled the path length. And so here I've worked that out. Essentially what you do is I'm doubling the path length. So this is the original path length. I'm multiplying it by 2. And then if you pull out that 2, this is the transmittance. You see that the new transmittance, T, would be the original transmittance squared. So you'd get 0.29 there. The last thing I wanted to emphasize about really the molar absorptivity coefficient is that it's not a single value. In fact, it's a function over the frequency of light. And so instead of seeing just a value when you're measuring transmission or absorption, in this case, when you're measuring absorption as a function of wave number of light, you don't just get a single value. You get a peak. And so the molar absorption coefficient it goes through a peak, and then oftentimes what you want to do is to calculate the area under the peak, and that's what this equation here is doing. It's saying you would integrate the peak. What I want to talk about next is the width of the peak. What are the factors that affect the line width of the peak? And so there's various factors that we can consider. One of them is just the quality of the instrument that we're using, the resolution of the instrument. If the instrument has poor resolution, then two nearby peaks cannot be distinguished from one another. And what you'll see is one doubly big peak. And so that will make the peak width appear larger than it actually is if you've got peaks that are merging together in the spectrum. We're going to focus on these other three broadening mechanisms here: Doppler broadening, lifetime broadening, and collisional broadening. So we'll start with the Doppler broadening effect. It's usually at this point in the lecture that I ask people if any of them live near the train tracks or have ever lived near a train tracks, because in that case they're very familiar with the Doppler effect. When the train's coming near you and it starts blowing its horn, you hear a high pitch. But then as the train passes you and moves away from you, you hear a lower pitch. Now, the pitch of the train's horn is the same, but because it's moving, you observe it at a different frequency. Okay, and this is called the Doppler effect, and it's one reason why you might see a broadening of the line width in your spectrum. So here is the expression for the observed frequency. S is the speed of the molecule relative to the detector. C is the speed of light. And then nu naught here, that's the actual frequency of the source. What we're doing is solving this equation for the speed. Okay, so just rearranging it, solving for S. And then what we're going to do for a gaseous sample is take advantage of the fact that we know what the distribution of speeds are for a gaseous sample. So we're going to make use of the kinetic molecular theory that we learned about in Chem 450. And basically, the distribution of speeds is going to be proportional to the distribution of frequencies. So our intensity profile as a function of observed frequency is going to look like the distribution of speeds, which is a Gaussian function here. Well, if you take the speed that we just derived from the Doppler effect formula and plug that in, you'll get a Gaussian function of observed frequencies. And it's going to look exactly like that. It's going to look like this curve. And so this is a Gaussian, and Gaussians are well-known functions, and they have a well-known width. And so using the Doppler formula and the distribution of speeds, you can derive this expression for the Doppler line width of a spectral peak. And the points to note are that it depends on both temperature, the square root of temperature, in fact, and it also depends on the initial, it depends on the frequency of the source, so nu naught. As temperature goes up, as we'll see here, so this is our peak at a given temperature T. As the temperature increases, the line width gets larger. As temperature gets smaller, the line width gets smaller. In this problem, they've asked us to calculate the Doppler line width for a sample of carbon monoxide molecules at 300 Kelvin. And this is the frequency that we're observing. Okay, so this is the frequency of light that's being absorbed. Here's the formula for calculating the Doppler shift. I put the frequency down here at the bottom on the left-hand side. And so you just need to plug in the mass in kilograms. You need to plug in the Boltzmann constant, the temperature in units of Kelvin, speed of light. Use SI units for all of these. And then you get your number. To get the actual line width for the peak that we're interested in, you then multiply this number, which is unitless. You multiply it by the frequency of interest, wave number in this case. And so you would get something like 5 times 10 to the minus 3 reciprocal centimeters. Or if you express that on the in terms of a regular frequency, it would be 151 megahertz compared to the 64.4 terahertz that we have for nu naught. Okay, so the Doppler line width under these conditions is not very large at all. It's fairly small, right? So 0.005 compared to 2150, so not very big at all. Although if you change the temperature, it would grow. On this slide, we're looking at the other two broadening mechanisms, and they both fall under the category of lifetime broadening. One is called the natural line width of a spectral peak. The other one is the collisional broadening. And both of these obey the same rule. That is, the spectral line width, so the line width of the peak, is inversely proportional to the lifetime of the state if it decays by spontaneous emission. So for the natural line width, what we're talking about is really the uncertainty principle. Previously in the course, we've looked at the uncertainty principle between two operators that do not commute with one another. For example, position and momentum, and that gives you the Heisenberg uncertainty principle, right? That you can't measure position and momentum simultaneously for any quantum system. Well, another version of the uncertainty principle relates essentially the line width of a peak to its lifetime, delta t. Here I'm going to be using the symbol tau to represent that delta t. And then we're going to convert the delta E to a frequency. So the width and frequency is the width and energy divided by Planck's constant. And then using this relationship, the minimum uncertainty in the frequency is going to be 1 over 2 pi times the line width. So as the lifetime of the excited state increases, the longer that excited state hangs around, the narrower the peak. Conversely, if you have a state that has a very short lifetime, then the width of the peak is going to be very large. Anyway, so natural line width refers to the minimum uncertainty, the minimum line width for a given peak. What can happen when you have a sample of molecules, a sample of excited states? These excited states, these molecules will collide with one another, and that those collisions can induce non-radiative transitions, which will shorten the lifetime of the excited state. And so what I have listed here, the lifetime associated with collisional broadening is going to be related to 1 over the collision frequency, right? So the collision frequency, that's another quantity that we learned about in kinetic molecular theory. It represents, it is the number of collisions per unit time. And since it's the collisions that cause the molecules to de-excite, the lifetime will be the reciprocal of the collision frequency. And last semester we learned about all sorts of relationships for calculating collision frequencies. They depend on the size of the molecules. So sigma is the cross-sectional area of the molecules that are colliding. This is a v, velocity, the relative speed of the colliding partners, how fast they're moving. P is the pressure of the gas sample, and then T is the temperature of the sample. The relative speed, we learned about all sorts of formulas for calculating different speeds associated with the kinetic molecular theory. The relative speed depends on temperature and the reduced mass of the molecule of interest, or of the collision pair, I should say. So the idea here, if you wanted to calculate the pressure broadening, this is called pressure broadening because it depends on pressure. If you wanted to calculate the broadening due to pressure, you would first calculate the relative speed, then the collision frequency, then you would take the reciprocal of that to give you the lifetime due to collisional broadening, and then you pop that into here to calculate the line width. And I think those problems like that are illustrated here in these two examples. The first one wants us to calculate the natural line width for an excited state that has a lifetime of 10 nanoseconds. So this is using this relationship here. They give us the lifetime, so we simply plug that in and calculate the line width. So 16 megahertz in this case, corresponding to about 10 to the minus fourth reciprocal centimeters. For the second example, we're considering pressure broadening in methane. The pressure is 1 bar, temperature is 298 Kelvin. They give us the cross-section. They're kind and even give us the relative speed. So we just simply plug all of those parameters into this quantity here. It gives us the collision frequency, so quite a few collisions per second in this sample, 10 to the 9th. And then you use that, you take the reciprocal of that collision frequency, that gives you the lifetime due to pressure broadening. So substituting 1 over z for tau gives us z over 2 pi. And we find that the line width is about 1.6 gigahertz in this case, which is several orders of magnitude larger than the natural line width for a state with a lifetime of 10 nanoseconds. Okay, so we've considered four broadening mechanisms. One is just how good the instrument is that you're using, and then the other 3, Doppler broadening, the natural line width, and then pressure broadening. Okay, so that's the end of the video, so I'm gonna stop it right here.